So in order to demonstrate some of these points about simple kriging, I'm going to show you a very simple example. And then in class, we'll solve a more numerical example. Here, it's more conceptual, okay? So I'm showing you 3 points. There's a point on the left, supposing you have some data there. And there is a point on the right, and supposing you have another data point here. And using these two data points, we are trying to estimate the value over here, right? So this is the where I put the question mark. That's the location where you're trying to do the estimation. And I told you that the user has to specify a covariance function. So I'm giving you the covariance function, right? So when a point is sitting on top of each other, of another, the points are perfectly correlated. It starts from a value of 1. And then as the distance between the points increase along this x-axis, the covariance starts dropping. It starts dropping. Now, in this covariance, I'm giving you a small thing called a nugget effect. What is this nugget effect? It means that when you go a little bit away from a point, you pick up some variability, some intrinsic variability in the phenomenon, right? So, and this might be coming about because, supposing, like to give this example. Supposing you have a pore, a small pore, right? And you are passing an X-ray through this pore. Now, and there is another pore over here, another set of grains over here. Now, if this pore and the next one is such that it is just slid over by a micron, so that this X-ray goes through the first pore, but then it gets blocked by a grain, then what will you think? You'll think that I have because X-ray has to pass through in order for you to deem an object to be porous, and because the grain is absorbing the X-ray, you will say that the porosity is 0 because no X-ray goes through the pore space. But then if the pores are shifted by a micron, they'll align each other. And so now when you shine the X-ray, it goes right through and you say that the porosity is 100%. Just by moving by a micron, porosity has gone from 0 to 100 micron, to 100%. Right? Now, that's an intrinsic variability of that phenomenon. And in the graph that I'm showing you here, these distances might be much larger, maybe in centimeters or meters. And so micron is something minuscule in the scale. And so you pick up this variability, this nugget effect, because it's the variability that you have in your sample is sub all the scales that you have. Right? So that's called a nugget effect. It's got some connotation why it's called nugget effect. The origin is from the diamond mining industry and things like that. I don't have time to talk about all that, but this is the covariance model. As the distance increases, the covariance drops. So I go back to my Kriging estimator. This is the form of the Kriging estimator that we had. In this case, I'm assuming that the mean everywhere is constant. So remember, I told you that in that case, the lambda 0 becomes 1 minus summation of lambda alpha times m. And then you have this lambda alpha times z alpha, the weight assigned to the two data. In this case, there are only two data locations. So I can expand this 1 minus summation, 1 minus lambda 1 minus lambda 2 times m plus lambda 1 times zu1 plus lambda 2 times zu2. There are only two locations. And the Kriging system is, again, a 2 by 2 system. There are only two data points. So you'll have two terms in the first equation, two terms on the left-hand side for the second equation. So you have a 2 by 2 system. And you can solve that very easily. Here, I'm just writing the entire thing instead of C, I'm putting rho because I'm saying that let's standardize the covariance, divide by the product of the variances and all that to make it a correlation. And it becomes easier to understand what that is. Because remember, I told you covariance is affected by the data, whereas the correlation coefficient is unitless, right? So just easier to work with that. So I have a 2 by 2 system of equations. This is how that equation will look like. On the right-hand side, the first equation is with respect to alpha equals 1. So you have beta equals 1 and beta equals 2, and then alpha equals 1. Second equation is with respect to alpha equals 2, and you have beta equals 1, beta equals 2. So this is something I mentioned in the previous segment. So you can solve this 2 by 2 system of equations, and you can write down an expression for lambda 1 and lambda 2, and the weight assigned to the mean. Remember, I told you that you can almost view this as a weight assigned to the mean is just 1 minus lambda 1 minus lambda 2. And so you can come up with the expression for the weight assigned to the mean. So now I have, this is my basic solution for simple Kriging. This is also giving you an idea of how you solve the Kriging system of equations and things like that. But what I want to do next is to play around with this expression, right? To show you some of the properties of Kriging by doing some interesting manipulation to this example. So the first thing I'm going to do is that I'm going to move the second data point to infinity. So I'm pushing it to infinity. Right? So I made H2, the lag H2, the distance from that second data point to that estimation node, I made it equal to infinity. I moved it to infinity. So if I move things to infinity by this covariance model, at infinity, when the distance increases to infinity, my covariance has gone to zero, right? The correlogram is going to be equal to zero. The relationship has completely disappeared because the distance has become too large, right? So rho h2 will be equal to rho d will be equal to zero. And if I put rho h2 equal to zero in this expression and this expression, then you can see that lambda 1 will come out to be exactly equal to rho h1, and lambda 2 comes out to be equal to zero, and lambda m is equal to 1 minus lambda 1 minus lambda 2, and I can put these two values and I can get lambda m is equal to 1 minus rho h1, right? So this becomes my Kriging estimator in that case. Z star of u equals 1 minus rho h1 times m plus rho h1 times zu1. Now, interesting thing is that rho h1 is nothing but the correlation between the data and the prediction. Rho is almost like the rho xy we had in linear regression. 1 minus rho h1 is also something like a correlation between the mean and the prediction that you're trying to make. So the point that I want to make is that when you move one of the data points to infinity, in other words, you have killed any communication between the data. So the data don't chat with each other. In that situation, Kriging becomes exactly linear regression. The information in your second piece of data is weighted by the mean, the correlation between the data and the unknown, which is exactly like in linear regression. So the earlier point that I made, that simple Kriging is nothing but linear, or linear regression is nothing but a special case of Kriging where you ignore the data to data interactions. This example, by moving one of the data to infinity, is just proving that. And furthermore, if I go to this Kriging variance expression, C0 minus summation of lambda alpha CH alpha 0, and I substitute what the lambda alpha was, which is rho H1 for one data point and 0 for the other data point, I will get sigma squared is equal to 1 minus rho squared H1. And rho squared H1 is, for Gaussian processes, will always be less than or equal to 1, right? So in other words, if you have a data point which is sufficiently close to your estimation node, your estimation variance is guaranteed to go down. Remember, in simple Kriging we said, hey, variance can go up if the data become chatting with each other. Well, when you make the data completely redundant, then the estimation variance always has to go down, right? But the fact of the matter is that in most estimation situations, data are not redundant. They will have some chatter. And so the estimation variance, you have to be very careful about making conclusions about whether it'll go up or down and things like that. So this simple example is proving those 2 points, that simple regression or simple Kriging is nothing but regression when the data become independent of each other. And when the data become independent of each other, the estimation variance is guaranteed to go down, right? But like I said, that may not be the reality, in which case, if you do simple Kriging, you'll get a false notion that variance is going down, uncertainty is going down, when in actuality it is not. Okay, so that's one variation of this example. What's the second variation we can do? Let's move both the data points to infinity now. Or actually, no, before we do that, I think did I miss a slide in the middle? Yes, did I don't know. Yeah, so in the next segment, I'll talk about another variation where you take the first data point, you move the second data point to infinity, but now the first data point, you're going to take it and put it on top of your estimation, right? So I'm making the estimation at the location where I have data. So I want to prove to you that Kriging is an exact interpolator, right? So I told you that Kriging is exact. You'll honor each single data point.